Hello friends, we have been looking into different thermodynamic functions and their variables, the variables which govern them. Now when we arrived at each of these thermodynamic functions, we saw that there were characteristic assumptions that we made in order to arrive at these functions, and we proceeded by relaxing all these functions, and finally we relaxed one of the assumption that undergirded all the different thermodynamic function. That is, we assumed while deriving all these thermodynamic functions that the system was a closed system, and when we relaxed that assumption, a new thermodynamic variable was introduced, and this we refer to as chemical potential. Now in the previous lecture we saw that while treating a material as a system, you need not have an open system for the mass transfer to govern a change in the state of the system. It is possible for us to have a closed system, and within the closed system it is possible for us to have a mass transfer governing the change in the state of the system. So that is what we saw in the previous lecture. Now let us take a step back, reconsider thermodynamic functions and their variables, and see if there are any simplification that can be made further. So we relaxed all the assumptions that we made so that it is possible for us to describe any change in the state of the system using thermodynamics. So it is possible for us to describe any dynamic system using thermodynamics. So once we have reached that level, we opened the system up and we introduced chemical potential. Now let us revisit our thermodynamic function and see if it is possible for us to make those functions and the variables more accessible. So one of the reasons we considered the thermodynamic functions was, in addition for us to enable or for us to describe a system or a change in the state of the system, any change in the state of the system, in addition to that, the reason we were focusing largely on the thermodynamic functions and their variables is primarily because we want to describe the state of the system or a change in the state of the system using variables that are accessible to us. So accessible meaning that are measurable to us. Now let us go back to thermodynamic functions and variables and see if all these variables are accessible, or can any variable be replaced so that the thermodynamic approach to a given system is more easier. So let us revisit the thermodynamic functions and their variables to see if it is readily accessible, or it can be made even more reachable, or it can be made even more approachable, so that these functions and these variables can be directly adopted without much difficulties. So in order to do that, let us begin by expressing all the thermodynamic functions we have considered so far. So we begin with the internal energy. The internal energy, it depends on a change in the internal energy. It depends on entropy and volume, and it can be represented as or expressed as TdS minus a constant pressure and change in volume. And the next thermodynamic function is the change in the enthalpy, which is dependent on the entropy and pressure, and the change in the entropy remains the same and the pressure changes, and is expressed in this way. Now we have the Helmholtz free energy, which is dependent on temperature and volume, and it is expressed in this manner. And we have Gibbs free energy, that is dependent on temperature and pressure. So change in the Gibbs free energy, that is dependent on temperature and pressure, which is expressed in this way. Now what we essentially have is, we have the thermodynamic functions that are internal energy, enthalpy, Helmholtz free energy and Gibbs free energy. So this rather constitute our thermodynamic functions, and the variables or the thermodynamic variables that dictate these thermodynamic functions are temperature, pressure, volume and entropy. So these are the variables that dictate the thermodynamic function. Now if you consider these functions, they are dependent on these variables. So if these variables are accessible, so that automatically makes these functions accessible, these functions approachable, these functions useful for us. Now if you consider these variables, so temperature, it is possible for us to measure. It is possible for us to measure the change in the temperature at a given temperature. The same applies for pressure and also for volume. So when you consider temperature, pressure and volume, so these are the variables, these are parameters that can be easily measured. A given condition can be measured, that a given temperature can be measured, a given pressure, volume can be measured, and the change can also be measured. However, the odd one out here, the odd one out of these four variables is the entropy, because for a given system, entropy is not that straightforward to measure. Even if you consider the canonical description of the entropy, wherein we need to consider the heat transfer and temperature, the entropy is not that straightforward to measure. Like, it is not as approachable or as accessible. So unlike temperature, pressure and volume, which we are familiar with, which we can be easily accessed, same cannot be said for entropy. So let us try to see if something can be done about it, or is it possible for us to replace this change in the entropy, or the way the entropy governs this function, is it possible for us to replace it with other accessible or other more easily usable variables. So in order to do that, let us begin by considering again with the thermodynamic function, the easiest one or the first one that we have considered, that is the change in the internal energy. So the change in the internal energy, it is dependent on two state variables, that is entropy and volume. So since these are two state variables, so the overall change in the internal energy can be expressed as change in the internal energy with respect to the entropy during constant volume, or assuming that the volume is constant, and change in the internal energy with respect to volume assuming the entropy is constant. So we have equation 1 here and we have equation 2 here. So now let us compare equation 1 and 2. We see that the left hand side of both these equations are equal, and when you come to the right hand side, you have certain common terms, that is ds and ds are common and dv and dv are common. So because of the similarity, we can directly state that the change in the internal energy with the change in entropy when the volume is constant is equal to temperature. So we are comparing 1 and 2 and we are arriving at the relation that change in the internal energy, so this term here, so we have ds and ds here, so therefore this term here and this term here should be equal. So that is change in the internal energy with respect to entropy is equal to the temperature, and the same goes for, because of the similarity in dv and dv here, the change in the internal energy with respect to volume is the negative of pressure. So change in the internal energy with respect to volume when the entropy is constant is negative of pressure. So let me rewrite it once again in a new slide. So what we essentially have arrived at is change in the internal energy with respect to the entropy when the volume is constant is the temperature, and change in the internal energy with respect to the volume when the entropy is constant is the negative of pressure. Now what we have is, we have related temperature and change in the internal energy, pressure and change in the internal energy, assuming here volume is constant and entropy is constant. Now let us try to relax that assumption. So when you relax that assumption, what you end up having is change in the volume with respect to the change in the internal energy as the entropy changes. So we are relaxing this volume constant assumption, and if you extend the same here, we are changing the entropy as the internal energy changes with volume. So we arrived at this expression, and now we are relaxing the constants that we assume when we arrive at this relation. So when we relax this assumption, that gives us this expression, then we end up with these derivative terms here. Now let us focus on these two derivative terms. So what we essentially have is, we have some double derivative of the entropy with respect to, or rather double derivative of the internal energy with respect to entropy and volume, the double derivative of the internal energy with respect to volume and entropy. So what essentially has happened is, just the order has been reversed. Now if you read, so what essentially we see is, we see in both cases there is a double derivative that has been achieved. What essentially has changed is just the order has changed. Now if you consider a simplistic example, say f of xy is say a constant, say phi xy. So f of xy is equal to phi xy. Now what you do is you take the partial derivative of f of x and with respect to, or f of so you take the partial derivative of the function with respect to x, and this assumes the y is constant. So that means this expression will give you the answer, rather phi y. Now when you take the y derivative of this partial derivative, then you end up having phi. So you initially take the derivative of the function with respect to x, and then this derivative, for this derivative you add the second derivative for y, and when you do that you end up with the constant which is phi. Now when we reverse the order, so we begin with the derivative of the function x with respect to y, assuming the x is constant, so that will give us phi x. So initially we consider the derivative of f with respect to x assuming y is constant. Now we are considering the derivative of f with respect to y assuming x is constant, so this gives us phi x. Now what we are attempting to do is, we are attempting to add another derivative by relaxing this assumption. We are now considering the derivative of x for this partial derivative, and when we do that we arrive at the same constant. Now what essentially this means is that whenever you are considering a second derivative and with respect to the relaxation of its constant, and if the order is reversed, the end derivative that you get remains the same, meaning for this function here f of x comma y, the partial derivative of x with respect to y and x is equal to the partial derivative of f with respect to x and y. So even though these orders are reversed, the ultimate derivative remains the same. So when the orders are reversed for the second derivative, the ultimate answer or the ultimate derivative remains the same. So essentially what you are considering is second derivative of the function f. So this is y with respect to y and x is equal to that of the second derivative of function f with respect to x and y. So if you apply the same rather straightforward equivalent relation that you observe for a second derivative of a function to this thermodynamic expressions that we have arrived here. So all these we have seen thus far are a simple numerical relation for a second derivative. So all these we have seen, these are just a simple numerical relation for a second order derivative, and we saw that even though we reverse the order of the derivative that we are considering for a second, for example for the second order derivative, despite the reversal the ultimate answer remains the same. So for a given order and this reverse, the derivative remains the same. So when you apply this numerical result for this thermodynamic derivatives, these thermodynamic functions, we end up having second order of the internal energy with respect to volume and with respect to entropy, which is equal to the second order of internal energy with respect to entropy and volume. So just the order is reversed, therefore these two second derivatives are equal. Now we have already arrived at a relation for the first derivative. So there is a negative sign here, so this negative sign needs to be carried out. So there is a negative sign here, so this negative sign needs to be carried over. So we have arrived at a constant for the first derivative. So if you substitute that constant for the first derivative, what you end up having is the derivative of the temperature with respect to that of the volume is the negative of the derivative of pressure with respect to entropy. So what essentially you have arrived at is, you have considered, so you have began with this simple relation wherein you have equated expression 1 and 2, you begin with this simple relation. So this relation is expressed here. Now you are relaxing this assumption that volume and here the entropy are constant. When you relax that assumption, you have to take or consider their change as well. So therefore you are considering the partial derivative of volume with respect to this term here. So this relation here, you are relaxing the constant constraint, and when you do that and you open up the bracket, you end up having second derivatives of the internal energy. Only in the denominator these orders are reversed. Since we are considering the second derivative of the internal energy with respect to volume and entropy, just the orders are reversed, we arrive at an equivalent relation. And now what we are essentially doing is, we are replacing the first derivatives with the corresponding constant which we have already arrived at. And when we do that, we end up having an expression that is, to rewrite what we have arrived at here, it is change in temperature with respect to change in volume is equal to minus of change in pressure with respect to change in entropy. So the way we arrive at this relation is what we refer to as in thermodynamically as Maxwell's relation. So this is what is referred to as the Maxwell's relation. So Maxwell's relation is nothing but the extension of a simple or rather straightforward relation between two second order partial derivatives. So if you look closely at Maxwell's relation, it just considers the second order derivative of a thermodynamic function with respect to two different variables. So Maxwell's relation is just considered second order derivative of a thermodynamic function. So Maxwell's relation considers second order derivative of a thermodynamic function with respect to its two variables, and what essentially is done is, these variables are reversed and an equivalency is established. And once the second order derivative with two variables which are reversed and equivalency is established, we arrive at a unique relation that relates all the four thermodynamic variables. So now we have arrived at an expression that relates all the four thermodynamic variables. So that is what we refer to as the Maxwell's relation. So what Maxwell's relation does is, it uses rather straightforward relations or straightforward properties, axioms of partial derivatives, and using that it helps us relate the four different thermodynamic variables. So that is what we know refer to as the Maxwell's relation, and a rather generalized expression for Maxwell's relation can be considered by this f of x function here. So a simple proof of, or rather a straightforward proof or easily understandable proof of the Maxwell's relation is given by this example here. So if you begin by considering a function that comprises of x and y, and you take the second derivative of this the f function, and then you observe the equivalency, and that is exactly what we are doing. But here, instead of considering any random function, we are considering a specific thermodynamic function, and instead of considering relating this function to an actual function, we are treating it as a function and relating the first derivative to a thermodynamic variable, and thereby we ultimately end up having a expression wherein we are able to bring closely or relate the four different thermodynamic variables. So now, even though we are now in a position to relate four different thermodynamic variables, we have not fulfilled or we have not rather reached our goal of replacing or playing around with this entropy. Because if you could recollect, at the beginning of this lecture, we saw that of all the four different thermodynamic variables that are related in this expression, one of the variable stands out, one of the variable is not particularly accessible. So we want to rather have a relation that helps us get rid of this particular variable. So that far we have not arrived at, but now we have an approach using which that goal can be reached. So let us see if that goal can be reached using this Maxwell's relation, using this Maxwell's approach. So in order to do that, let us begin by considering one of the thermodynamic function wherein the entropy is rather constant. So entropy is not a variable, one such thermodynamic function. So what we essentially want to do is we want to replace entropy as the fundamental variable with other variables, because entropy is not that easily measured. So that is our primary goal. So that is what we set out to achieve. Now in order to do that, we will consider a thermodynamic function wherein the entropy is constant. So if you consider the expression for the change in the Helmholtz free energy, it is expressed as S dt minus P dV. So this is the expression for the Helmholtz free energy. So according to this expression, the Helmholtz free energy is dependent on temperature and volume. So let us expand this expression based on its fundamental variables or the governing variables. So correspondingly, it can be expressed as change in the Helmholtz free energy with respect to temperature when the volume is constant, plus change in the Helmholtz free energy with respect to volume when the temperature is constant. Now let us consider these equations, that is 3 and 4. From 3 and 4 we can state that, so since on the left hand side we have the same terms, on the right hand side again we have dt, dt, dv, dv. So therefore minus s should be equal to this partial derivative here, and minus p should be equal to this partial derivative here. So let us consider that. So minus s is equal to the partial derivative here, that is change in the Helmholtz free energy with respect to change in temperature, and similarly minus p is equal to change in Helmholtz free energy with respect to change in volume. Now again, for this the volume is constant, for this the temperature is constant. Now let us relax this condition here. So that means let us relax this condition. So it would mean that we are considering change in the volume as well for the existing partial derivative. So we are taking the step that we have already taken for the Maxwell's relation. To arrive at the Maxwell's relation, whatever steps we have taken, we are adapting it. So when we relax this volume constant, we end up with this expression that is nothing but change in the entropy with change in the volume. Now, so this expression leads to this expansion here. Now let us do the same for this expression here. So it means the change in the pressure with respect to change in the temperature will be the second derivative of the Helmholtz free energy with respect to temperature and volume. Now let us consider these equations, that is 5 and 6. So let us compare the equations 5 and 6. So on the right hand side of the equation, what you essentially have is second derivative of the Helmholtz free energy with respect to volume and temperature here in equation 5. Here we have second derivative of Helmholtz free energy with respect to temperature and volume. So all that we see is the variables have been reversed. So we have arrived again at a relation that can be equated. So 5 and 6 are relations that are equal to one another. So therefore, since the RHS of the equations are equal, so that means the LHS should be equal. So the combination of these two yields a relation that minus of change in the entropy with respect to volume is equivalent to minus of change in pressure with respect to temperature. So these minus can be cancelled. So what essentially we end up having is change in entropy with respect to volume is equal to the change in pressure with respect to temperature. So what essentially we have arrived at is an expression that talks about change in entropy, but it does not need for us to measure the change in the entropy, but we can do, or we can equate the change in the entropy to that of change in pressure. So when you have a system that is exhibiting a change in an entropy by changing its volume, then instead of rather describing the change in the state of the system by considering the volume change and the entropy change, it is now possible through the Maxwell's relation for us to describe the change in the state of the system using the pressure and temperature. So change in the pressure and temperature. So supposing again you are observing a system that is exhibiting a change, and that change is rather represented by entropy and volume. So it is possible for us to manipulate the description in such a way that the same change can be expressed in terms of pressure and temperature, the variables that can be easily measured by us. So this is one way of describing or rather relating the change in the entropy. However, we need to know that this is rather restrictive because we are talking only in terms of change in entropy with respect to change in volume. So this relation here helps us describe or helps us get rid of measuring the entropy only when the entropy is changing with respect to volume. It is also possible the entropy can change with other variables as well. Now let us see if there is any other function that we can work on in order to arrive at similar expression. So if another thermodynamic function, if you could consider, or if you could recollect another thermodynamic function wherein the fundamental variables are different from entropy, wherein the entropy is constant, like here is the Gibbs free energy. So similar to the Helmholtz free energy, in case of Gibbs free energy, similar to the Helmholtz free energy, the entropy is constant. So let us consider how the Maxwell relation based on the Gibbs free energy can be arrived, so that any change in the entropy can be replaced by measurable thermodynamic variables. So we will carry out the same numerical operations that we performed for Helmholtz free energy on Gibbs free energy to see if it is possible for us to arrive at an expression that help us replace measuring the change in entropy. So let us begin by expressing the change in the Gibbs free energy. The change in the Gibbs free energy is expressed as minus S dt plus V dP. So this is how the change in the Gibbs free energy is expressed. Now the change in the Gibbs free energy is dependent on temperature and pressure. So that is what we observe here. And when we expand this or expand this expression here, what we end up having is change in the Gibbs free energy with respect to temperature when the pressure is constant, plus the change in the Gibbs free energy when with respect to pressure when the temperature is constant. Now then again we see the left hand side of the equations are these two equations. Let us call it as 7 and 8. So the left hand side of these two equations are equal, and we also find that there is dt present on the right hand side and dp present on the right hand side. So therefore by comparing the expression 7 and 8, we can state that, or we can arrive at this relation, that the change in the Gibbs free energy with respect to temperature is negative of the entropy, and change in the Gibbs free energy with respect to pressure is volume. So this relation here we have arrived at by considering these two expressions 7 and 8, and from these two expressions we have seen that change in the Gibbs free energy with respect to temperature, again when the volume is constant, is equal to the negative of the entropy. Change in Gibbs free energy with respect to pressure when the temperature is constant is equal to volume. Now let us proceed by considering or by relaxing these two constants by taking the numerical approach that we have adopted for to arrive at the Maxwell's relation. So when we do that, so when we relax this volume constant assumption, then we end up having considering the second derivative of the Gibbs free energy with respect to volume and temperature, and here as well we will be considering the second derivative of Gibbs free energy rather. So we have to relax this. So Gibbs free energy with respect to temperature we have to consider, and the second derivative of the Gibbs free energy with respect to volume. So this is ultimately what we end up having when we consider or when we extend the numerical operations that we did for Maxwell's relation to the Gibbs free energy. Pardon me, there appears to be a mistake here. That is, when you consider the previous slide, it is the P that is constant, the pressure that is constant, and the temperature that is constant. And here I have written it as volume, so it should be P. The pressure is constant, and here the temperature is constant. So therefore, here the second derivative of Gibbs free energy with respect to pressure and temperature, and here what we essentially have is the second derivative of Gibbs free energy with respect to temperature and pressure. So here pressure and temperature and pressure. So essentially what we have arrived at is we have in both these cases considering the second derivative of Gibbs free energy only, as we have seen in the previous numerical treatment of Maxwell relation, the order of the variables are reversed. So therefore from these two we can state that the change or the negative of the change in entropy, so this negative, which we are just carrying it over from the previous expression, the negative of the change in entropy with respect to change in pressure is equal to the change in volume with respect to temperature. So essentially what we have done is we have just followed all the numerical operation that we followed while we have considered the Maxwell's relation. That is all we did. So only confusion here was, pardon me, instead of pressure I have introduced volume. So that is the only confusion, but nevertheless apart from that we approach the line that or the numerical treatment that we did for Maxwell's relation is the same has been carried over for the Gibbs energy as well. And when we do that, we begin with the partial derivative of the Gibbs free energy related to a specific thermodynamic variable, and then take the second derivative of the Gibbs free energy, and then we arrive at this expression here. So what this expression, if we write this expressions out separately, what we essentially have is the negative of the change in the entropy with respect to pressure is equal to change in the volume with respect to temperature. So this is a relation that attempts to equate the change in the entropy with respect to pressure in terms of, or it relates this change in this entropy with respect to pressure to the volume and temperature, the change in volume with respect to temperature. So the change in entropy with respect to pressure is related to an accessible variable or accessible parameters in this expression here, and the same we have seen here wherein the change in the entropy now with respect to volume is related to accessible variables of pressure and temperature. So if we write this expression here, if we rewrite this expression, so here in the previous expression we saw change in the entropy with respect to volume. Now just rewriting this expression is equivalent to change in the pressure with respect to temperature. So we have arrived both these two expressions from, so this one was from the Helmholtz free energy and this one is from the Gibbs free energy. So what we have essentially done is using the numerical operation or numerical treatment that is associated with the Maxwell's relation, now we have arrived at two equations that relate change in the enthalpy to change in accessible or most easily measurable variables. So these easily measurable variables are volume, temperature and pressure. So we are now in a position to relate change in the entropy with respect to change in the volume or change in the pressure. So change in entropy with respect to pressure can be related to volume and temperature. Change in entropy with respect to volume can be related to pressure and temperature. So these relations are possible through the Maxwell's relation. So these equivalency or these ability for us to treat the change in the entropy or replace the change in the entropy with more easily accessible variables has been possible through Maxwell relation. So again, Maxwell relation, it largely depends on the foundation of the Maxwell relation is when you consider a second order derivative of a thermodynamic function and you reverse the variables, then despite the reversal of the order, it remains equivalent. So from that understanding of Maxwell's relation, now we have arrived at two expressions which can largely be used to replace the change in the entropy with a more approachable or more measurable variables. Now let us put these expressions into practice and see if it actually does the job. So far we have been theoretically stating, okay, we have these set of variables. These set of variables include volume, temperature, pressure and entropy, and we saw that, okay, even though it is easy for us to measure volume, temperature and pressure, it is not that straightforward to measure entropy, so we want to get rid of it. So in order to do that, we went into Maxwell's relation. We understood what Maxwell's relation is, and that Maxwell's relation now has given us two equations or two relation to expression that seems to help us in the task of removing or getting rid of the dependency on entropy. Let us put this relation to practice, or let us see if these relations does the job. So in order to do that, in order to see if this relation does the job of removing the dependency on entropy, let us consider a thermodynamic function which is dependent on entropy. So what we want to do is we want to try to measure a thermodynamic function that is dependent on entropy without directly measuring it. We want to get rid of a thermodynamic function or a dependency of a thermodynamic function on entropy. Again, because entropy is not that straightforward to measure. So one of the thermodynamic function that is dependent on entropy is none other than the internal energy. So if you could recollect, we began with the expression for the internal energy, and it is fundamentally dependent on the entropy here. So therefore, let us see if we are able to replace or if we are able to manipulate this dependency of the internal energy on entropy. So in order to do that, let us begin by writing the expression for the internal energy. So it is dependent on the entropy and volume. So it is Pdx minus Pdv. So this is what we have seen, or the first expression that we have seen in this lecture. Now what we will try to do is, we will rather try to replace or to consider the change in the volume replace or get rid of this dV term here. So change in the volume, let us attempt to get rid of it, meaning we will divide the whole of this equation by dV, or we will consider the change in the volume for all the terms that are involved. So we will consider change in the volume for this term and all the terms. So that means we are considering the change in volume for the left hand side and also for the right hand side. So thereby we are not having any bias treatment, we are not considering any bias treatment or a neutral numerical treatment. So when you have such a cancelling out or numerical treatment or an unbiased numerical treatment, what you essentially end up with, so you are trying to introduce this change in the volume both on the left hand side of the expression and also on the right hand side of the expression. So you are trying to introduce this change in the volume both left and right hand side of this expression. So what you would end up having is change in the internal energy with respect to change in volume. Again, we are trying to introduce change in volume in both left and right hand side is dependent on these terms, that is T, change in the internal energy with respect to change in volume, and T is constant, so change in the entropy with respect to change in volume minus just P, because these when you consider the change in the volume both left hand side and the right hand side, this change in volume gets cancelled out, it gets removed. So you end up having an expression like this. So in order to arrive at this expression, again we are just considering change in volume both left and the right hand side of the expression. Now when you look closely, what you observe is in this term here, so here what we have is change in the entropy with respect to change in volume, and this is nothing but change in pressure with respect to change in temperature. So essentially this term here can be replaced by this term. So this term here can be replaced by this term. So this relation that we got from the Helmholtz free energy can be substituted here. So therefore the change in the internal energy with respect to change in the volume is equal to temperature, change in the pressure with respect to change in the temperature minus pressure. So what essentially now we have is, we have now an expression that talks about the change in the internal energy not in terms of change in the entropy or change in volume, but in terms of change in pressure and in change in temperature. So essentially we have removed, or we have rather replaced the dependency of internal energy on entropy by with the pressure and temperature. So essentially now internal change in the internal energy is no longer dependent on the entropy, but it is dependent on change in pressure and temperature. Now if you compare these two expressions, when you see a system that is exhibiting a change in the internal energy as its volume changes, so in order to quantify that change in the internal energy with respect to the change in volume, when you have this expression alone, so this expression here is just another way of writing this actual original expression. So this canonical expression has been written in this way, and when you have this expression here alone, the change in the internal energy of the system with respect to volume can only be expressed or can only be described while considering the change in entropy, while the change in the entropy is known. Now using Maxwell's relation, we have arrived at an expression wherein even without considering the change in the entropy, it is possible for us to describe the change in the state of the system or change in the internal energy using the measurable change in pressure and change in temperature. So pressure and temperature we are already considering, and change in pressure with respect to change in temperature, by considering that, by estimating that, which again is more accessible than the entropy, it becomes rather straightforward for us to describe the change in the internal energy or the change in the state of the system with respect to change in volume. So this is the critical role. So whatever we have set out to do, so this lecture began by, we wanted to replace the dependency of, or the influence of entropy, the direct influence of entropy on a thermodynamic function. So we want to replace that entropy variable with other accessible variables. So now at the end of the lecture we have arrived at this expression here, which shows that, which indicates that the change in the internal energy with respect to volume can be, even though initially it is dependent on entropy, it can only be known by measuring the change in the entropy. Now we have arrived at another expression that helps us understand or quantify the change in internal energy with respect to the volume just by measuring the change in pressure with respect to change in temperature. So when you consider the variable that dictates the change in this thermodynamic function in this expression, these variables only include volume, pressure and temperature. So these are the fundamental variables that dictate the change in the internal energy. So we set out to remove the influence of entropy, and now we have arrived at it. So we have now established or derived an expression wherein the change in the thermodynamic function is no longer dependent on entropy. Without measuring the change in the entropy, now it has become possible for us to rather quantify the change in the internal energy when there is a change in volume. Now there is another thermodynamic function that is dependent on the entropy, and that thermodynamic function is the enthalpy. So the enthalpy, similar to that of the internal energy, is also dependent on entropy and the pressure. So it is rather written as TdS plus VdP. So this is the expression for the enthalpy. So similar to the internal energy, we have this expression here. Now what we need to do is, what the approach that we need to adapt rather is, we need to adapt the similar approach that we have taken for, or similar numerical operation that we have considered for the internal energy. Now what we need to do is, we need to consider the change in pressure both along the left hand side and the right hand side of the expression. So we need to consider change in pressure both in the enthalpy and also these combinations of terms. When we do that, we end up with this expression, that is change in enthalpy with respect to change in pressure is equal to the constant temperature, change in entropy with respect to change in pressure, and V. So we have performed the same numerical operation that we performed in the previous case. Now what we need to do is, we need to get rid of this term here, because this is the term that introduces the influence of entropy on the change in enthalpy. So in order to get rid of this term, let us go back and see if we have arrived at any similar relation. And fortunately by considering the Gibbs free energy, we have arrived at this relation here. That is, if we rewrite this relation, that is the negative of change in entropy with respect to change in pressure is equal to change in volume with respect to change in temperature. So this expression, this Maxwell's relation, we arrived at from the Gibbs free energy, and when we substitute this here, we can express the change in the enthalpy with respect to change in pressure as the negative of the product of temperature and change in volume with respect to change in temperature plus volume. Now again, we have ensured that the change in enthalpy is no longer dependent on entropy, but it is just dependent on volume and temperature. So in both the cases, so originally both enthalpy and internal energy, they were dependent on entropies, and now through Maxwell's relation we are in a position to express the change in both enthalpy and internal energy in terms of more accessible variables, that is temperature, pressure and volume. And like we stated in the initial stages of the structure, we were now able to get rid of the entropy as the dependent variable because it's rather quite hard or difficult to measure. So this is the advantage, or this is the pivotal role of Maxwell's relation. So the Maxwell's relation help us in describing or measuring the change in the thermodynamic function. So without the Maxwell's relation, it still becomes rather quite difficult for us to quantify the change in the internal energy and change in the enthalpy for a physical system, because to measure change in entropy is quite difficult. So with the help of Maxwell's relation, we have replaced the influence of entropy through these variables that can be easily measured, and therefore it becomes possible for us to measure or to describe a physical system based on the internal energy, a change in the internal energy and change in the enthalpy. So this is the key role of Maxwell's relation. So Maxwell's relation, when you consider it from a numerical standpoint, it is rather straightforward. It just considers the second order derivative of a thermodynamic function with reversed treatment of the variables. Despite a rather straightforward outlook of the Maxwell's relation, particularly from a numerical standpoint, it has a pivotal role when we are trying to relate the thermodynamic functions to physical system, because it helps us get rid of the influence of the entropy and it helps us replace it with appropriate variables that can be easily measured. So with this, we will wind this lecture up, and in the subsequent lecture we will look into the further new additional aspects of the thermodynamics. Goodbye.